minutes to talk about your research. All right. So,
Okay.
Dr. Panpan Zhang is an assistant professor of biostatistics at Vanderbilt University. He got his PhD in statistics from George Washington University. His research interests include network data analysis, applied probability, longitudinal data analysis, missing data applications in Alzheimer's disease and neurodegenerative disorders. Panpan, you can get started. Thank you.
Thank you so much for Zhang for the very kind introduction. And I'd like to thank Zhang and Warren and a bunch of UNC people who are dedicated to organizing this workshop. It is a little bit unfortunate that I'm not able to attend the workshop in person because my family members, they got the COVID, so, and I'm also at risk. So, but anyhow, it is my greatest pleasure to briefly introduce one of the projects in progress, which is about the analysis of functional brain networks with the presence of erroneous links. And I will try to make the presentation short so that you can get into the next section and that do this as soon as possible. So just like three brief sections, introduction, method, and the discussions. So introduction. So my background, as Zhang introduced, is more about theoretical and theoretical statistics. So my thesis was more focused on the network analysis to social network data. And so network is a mathematical graph with nodes and consisting of nodes and the links. And there are quite a lot of challenges in network data analysis in general. And I'm listing a couple of very good challenges over here. And this particular research is focusing on the challenges arising from data quality. And the functional brain networks are becoming a prominent tool for analyzing neural data. And because I'm affiliated with the Vanderbilt EPIC, so we do notice that the neural data available for improving the diagnosis and the prognosis of chronic neurodegenerative disorders like AD. And this research actually was inspired from some graph theory-based analysis methods to analyze functional brain networks. And one of the featuring papers is authored by Sabati back in 2019. Actually, some earlier work, some pioneering work was authored by Dr. Zhang from Wake Forest University back in early 2010s. And functional brain networks are constructed from the functional magnetic resonance imaging data, and it consists of nodes which usually represent regions of interest, and the links estimating the functional connectivity. And so one of the major parts of the functional connectivity, functional brain network analysis is the estimation of functional connectivity. And in general, it is based on the bold signals which stems from the vasculature. So the bold signals is an indirect reflection of neuronal activities. And one of the traditional methods, classical methods, is to use the correlation of the time process of voxels or the regions during the resting state to estimate functional connectivity. And usually when the two ROIs with a high correlation, they are both time courses during rest are seen to be functional connected on the neuronal level. And the motivation of this particular study is to concern about the emergence of erroneous links in functional brain networks. And here are the erroneous links we can think it of as like measurement error problems. And so we can kind of like consider both false negative and the false positive links. And here, it may not be precise like say the false negative links and missing links because they are conceptually different, but I mean, they are somehow similar. So the missing links can be observed. The missing data can be observed due to various reasons. One could be the data noise, or some of the data could be undetectable due to the technical limitation during the data acquisition, and sometimes because thresholding is one of the common techniques in a lot of downstream analysis, and while a threshold is implemented, it could also cause some mislinks. On the other hand, the spurious links could emerge due to the inflated functional connectivity during the courses of fMRI scans at spatially heterogeneous rates. So, like the motivation of this study to see how can we deal with the erroneous links, reasonably and brilliantly in functional brain network analysis. And here I am not really considering some other, motion artifact removal methods like aroma. These are things I would assume like these erroneous links will stay even after we apply some other, standard approaches in the pre-processing procedure. And here just like a very quick literature review. And so the limit prediction problem actually is a very common and popular problem in network analysis, not necessarily for neuroimaging studies. And so most of the existing networking prediction methods actually they were summarized in this sociological journal paper, and back in 2009, and they are all ad hoc, so they are not really providing any reliable statistical inference. And some advanced methods are based on node similarities quantified by structure-based network topology and observe the node covariance or both. And here I'm listing like 4 papers over here, and the top 3 actually they are all for social network analysis. And actually the paper that literally motivated this study is the last one. That's the paper authored by Dr. Shuo Chen from University of Maryland and his student Chong Wu, and back in 2021. And I think this paper, this article also won the SMI best student paper competition in that year. So, but in this paper, they were only considering this. So the overall research goal is to propose a network model accounting for observed node covariance linked to the node positions as well as the node heterogeneity simultaneously. And this is literally a misclassification problem because we are only looking to binarize the brain network, and the method can be effortlessly extended to weighted networks. And we developed a Bayesian estimation framework, and we also created our package for implementation. And I'm just going to quickly skip these notations and just to give like a quick review of this exponential random graph model. So just by looking at this formula, without even looking at the details, and we can see that this is an extension of the logistic regression. The difference is that the model considers both node covariance as well as the sum of the network topologies. And our approach is to extend the latent space model proposed by Mark Hancock and his group back in 2007. Actually, the latent space model originally was proposed by Peter Hoff and his group back in 2002 in his JASA paper. So this is still like a logistic regression model extension, but by considering 3 components. One is the component is specifying the contributions of the observed node covariance, and this SIJ is a similarity measure. And the second part is the latent positions, which is related to the clustering membership of the nodes. And lastly, these theta and theta they are just random effects and reflecting some nodal heterogeneity. And because the error extent model, we do know that we can use standard Bayesian methods for the inference, and this is how we are going to do. And here are some very quick takeaway notes, and just like a quick summary for the takeaway notes. This distance function, in our current study, we are considering the Euclidean distance, but for some other well-developed metrics, such as the inner product distance, it also can be used. And the Sij, this the similarity measure can be precisely specified by the researchers. And for the misclassification structure, I mean, supposedly A is the truth and O is the observation. So this is a very simple standard misclassification structure. And there can be different types of misclassification rates. It can be constant, and just like removing some indices I and J here, but it can be link-based or cluster-based. When it is cluster-based, it can be more challenging because of the change of the dimension. And the likelihood is very straightforward, and this is just like more like a moving model, kind of extended moving model. And the estimation strategy we're considering MCMC algorithm, and the determination of K, which is the total number of clusters, is to use sub-model selection methods. And here are just like the list of the prior specifications, and some of them can get, we can get the conjugate family directly, and all the rest we are just using the complete statistics algorithm. And we check the convergence by using the standard MCMC diagnostic plots. And there are some post-processing methods need to be used because of the model identifiability problems, and the model selection of K is based on the WNSC. And some quick discussion, I'm just listing one of the simulation results. We have quite a lot of simulations, and the algorithm is working well, even though it's CMC basis, not very fast. And just by looking at the estimates, bias, and the coverage probability, I mean, the algorithm is working okay. And we'll also provide some ROC and compute some the AUC to given the ground truth in our simulations to demonstrate the applicability of our method. And our application is to use data using that HTTP multiple scans so that we are able to do some recommendations. And here just a very quick summary of the future works. And first of all, we want to finish this project. And currently, we are just considering some simpler misclassification models. Probably we can consider more complex ones. And the extension to weighted networks is not very difficult. And we are now having one student helping us to develop the variational based algorithms, which will, make, increase the estimation speed a lot. And there are some dynamic estimations of K methods available, and we are trying that. It will not perform very well so far, maybe because of that, we are now having too many parameters. We are trying to figure out the better way. And we are also looking into some non-dimensional methods, which may help us, to develop some more robust approaches. And here are just some quick references, and I think I'm about time, so I will just stop here. Thanks so much for your attention.
Thank you, Panpan. I know you just